Moment of inertia of this blob on disk as it spins around the center here. If you recall back to last week, moment of inertia is just, you're adding up a whole bunch of mr squared, so in essence this is just I of the disk plus I of the blob. As we got a formula for both. What is the formula for the moment of inertia of a disk spinning about its center?
Is that I plus? Or
Yeah, that's supposed to be a plus sign. I am assuming that the size of the blob is small compared to the size of the disk.
I wasn't there last week.
Can someone help Latoya out? I assume you watched the video over and over again. With the kids. You want to see something scary for Halloween?
So are we supposed to find the radius and then add that to the blob?
What you're going to do is you find, for a moment of inertia, you're going to find the moment of inertia of the disk and the moment of inertia of the blob, and just add those two numbers together.
I think that's probably what I was getting at, so it would be like, 2 pi times the 2.
No, that pi actually does not show up here. I was hoping somebody was going to find the formula for the moment of inertia of a disk. So apparently, it's not happening. One half mr squared.
We just said that just a second ago.
Oh, I'm sorry. And then the blob, it's just a mass hanging out there, because remember the moment of inertia comes from just all the mr squareds. And so I have this mass that's all pretty much the same distance away. So that's just the mass of the blob. So this is disk here. This is mass of the blob times however far it is from that center. Just in essence, radius of the disk squared. It's because it's that far away from the middle. So this just becomes 1/2 times 4 times 2 squared plus mass of the blob, which is 3, times how far it is away from the center, which is 2 squared. So 8 plus 12 or 20. I'm feeling decent enough in math. All right, here's the tricky question. What's the units? What are the units?
What were we looking for again?
Ultimately, I'm going to be connected back to angular momentum, but I haven't gotten there yet. Right now, just what is the moment of inertia of this blob on a disk?
Is it meters per second?
No, not meters per second. Think about what we multiplied in order to get to it. What do we multiply?
Radius.
Which would have units of?
Radians per second?
Degrees?
Time actually does not show up in this. Pardon?
Degrees? No.
Radius. The distance from here to here. Units.
The kilograms? Or meter squared?
All right, so was the original question answered? Did you say, what did you say again?
I said our kilograms meter squared or.
Okay. This is mass, units of kilograms. This would be in meters squared. So it's kilogram meter squared. That's the units of the final answer. All right.
So, one second. So, Cause we just went all around that and we did not pay attention to, it was kilograms meters squared. So what we really need to be paying attention to when you asking us that is what you have picked up after it says radius equals 2 meters and the mass is 4 kilograms. When you asking us that, we should be looking at that point so we can find out what the units are.
If you don't know, then absolutely.
Okay.
As long as if I'm always dealing with kilograms and meters, then
Mhm.
moment of inertia or rotational inertia is always gonna be kilogram meter squared.
Mm-hmm.
So, at some point, you might get to the point where we're going, oh, moment of inertia, kilogram meter squared. But if that blanket on that, then it's going to, all right, units of mass, oh, kilograms.
Mm-hmm.
Distance, oh, meters squared.
Okay.
All right. That was just a little side note, bring back some fond memories of last week. So now, I'm gonna have this thing spinning around, this disc with a blob spinning around at, what number have I not used? I haven't used 5 yet. So 5 radians per second. So 5 radians a second, so about that speed right there. So the question is, what's the angular momentum? Well, we got a formula right there.
Wouldn't it be 20 times whatever omega is?
Yes, and what is omega?
Is it 5 radians per second?
Indeed it is. So this is 20 kilogram meter squared times 5 radians per second.
That looks very similar to inertia, like the symbol for that. Is that what it is, or?
Oh, that right there?
Yeah.
Yeah, no, they are not supposed to look alike. That's supposed to be a capital L.
Oh, okay.
I do recognize that some of my eyes look kind of like L's. So the math part is just 20 times 5, as Rebecca had said.
100.
And what are the units?
Kilograms times meters squared.
There's also radians per second.
We got radians squared?
There's no radian squared.
Oh, sorry. Oh,
Is it-
radian per second. Let me mind my business, go ahead,
Is it all of them together?
Yeah. What are the units?
Kilograms times meters squared radians per second.
That's a lovely unit, isn't it? It's just that times that.
Who came up with that?
They have not come up with a single word unit for that. That's just, it's a mess. We
So-
can make it a little bit simpler, because radians we can actually get rid of or put in whenever we feel like it. So you actually could drop radians from that, and it's 100 kilogram meter squared per second. That's also legitimate. It's still an ugly looking unit, but that's the unit.
Okay.
If
And
we're
go right
doing
back
it,
to what I was saying, the reason why y'all got all of that, cause y'all put all of them together,
Mm-hmm.
all
Yeah.
the units together.
That pretty much, yep.
Okay,
Units multiplied just like fractions do.
if we're
Multiplying
doing
fractions.
a problem of these, can we just define a unit for this like we did earlier?
Yes.
Class, we don't have to write it.
See, what's a unit we haven't used yet?
Alpha?
Ooh, that'll get confusing,
Oh,
I
never
think.
mind.
So we use C for, what'd you say?
That was on me. I think that was wrong.
Me and my bad hearing. C is used for Coulomb, so that's been, pretty much a lot of the letters been used already. How about? I think we would be, oh, there we go. We're gonna define that as a kilogram meter squared per second. Does that work for you?
I'm not sure if that's easier to write or not.
I was about to
Yeah.
say, y'all,
All we need
What
to
is
know
that
the
exactly?
I.
What is this?
Yeah.
Well, since Jesse said it, I was gonna go with a C, but we use C for something, so then I put a line through it, but then it was the cent symbol, as in 5 cents, and so then I just stuck the other line through it.
and this means kilograms
meters squared per second.
How is there?
Meters squared per
And it's
second.
not necessarily, you know, it's not a legitimate unit other than the fact that I've defined it right there.
Mhm.
All right, so we have the angular momentum,
Can we use it on the test?
as long as we define it at the top. Now, through some mysterious process, this blob moves in to halfway. How fast is this thing spinning around now? We assume it's a closed system, so momentum is conserved, angular momentum is conserved. So in essence, my moment of inertia is going to get smaller because I have this blob moving in closer. Because the moment of inertia gets smaller, my angular velocity is going to have to go up. It's that balance, because I got the two things here. If it's conserved, then if one goes up, the other one goes down, so that I still get the same value. So now that the blob is halfway in between, the only thing that's changed is this number right here. It's now 1 meter from the center. It changes that number to 3. The beauty of being able to erase. So by just moving that blob halfway to the middle, we have taken our moment of inertia from 11 kilogram meter squared, or sorry, from 20 kilogram meter squared to 11 kilogram meter squared. Apparently, I'm not used to saying those words. So L initial is equal to L final. That's conservation. Whenever I prove one point, got another point. This was my I initial, omega initial. Equals I final, omega final. Because that's the formula. So this was 20 times 5 is equal to 11 times whatever my final angular velocity is. That's the math problem we're working with. I have my total L beforehand is equal to the total L afterwards.
$9.09. Kilogram meters squared per second.
No. This would be kilogram meters. So if we don't go that route, you got this by doing 100 divided by 11, I assume. So that's 100 kilogram meters squared per second divided by 11 kilogram meters squared.
Seconds.
Close. You're right that the kilogram and meter squared cancel out. But we're left with not just seconds.
Just meters per second?
No, not that far.
Radians per second?
Technically, it'd be 1 over seconds, but again, we can stick radians in or take it out. It is traditionally radians per second. It was radians per second to begin with, radians per second at the end. If you wrote 9.09 per second, it's not technically wrong. And some textbooks will do that. Personally, I find it really confusing when they write per second without something in the top. All right, so that's the math problem. I probably should have started out with the demonstration first, but what I wanted to get towards here is that if angular momentum is conserved, then these two are linked together, and if one goes up, the other one drops. And most of you probably have seen this, but we will do this. I'm gonna bring in the spinning chair, and I will try not to throw up in front of you, but at least I have a mask on so you won't see it. And hopefully this won't kick in my vertigo.
Uh-oh.
Your who?
Vertigo? Two balanced books probably would be helpful. Yeah, they're about the same. All right, so I'm gonna start out, spinning around, I'm gonna start out with them out like this. So think about my moment of inertia. My body has a certain mass that, axis of rotation right about here, and there's mass mainly distributed around the center. I take these two masses and I stick them out here, so that really adds on to the moment of inertia, because the radius, because it's squared, has more impact than just the mass does. Because my mass is definitely more significant than the books, but the books are farther away from the axis. Just like over here, when the blob was on the outside, this was the dominant factor in the total moment of inertia. And as I moved it in, it became less dominant. All right. As I spin around, I'm going to bring my arms in. So the moment of inertia gets much smaller because the distance from the axis to the book suddenly shrinks a great deal from whatever that distance is to this distance. And so what should happen is, since my total moment of inertia drops, my speed should go up. And I don't know how to spot, which is one of the reasons why I get dizzy. And then pause.
Can't take you to the carnival.
Yeah, at some point, it's it's gonna hit most of you at some point in your life. Just you wait. All right, so anyway, so as I'm spinning around, from an angular momentum point of view, it's called conservation of angular momentum. If you've seen figure skaters do spins, it's exactly the same thing. When they start with their arms out like this, they bring it tight. Or
And then they start to go faster when they bring this in tight?
Yep,
Oh, I love watching figure skating too.
it's conservation of angular momentum.
So
Or
when they put their arms out, they kind of like slow down a little bit more?
Yep. And you might have experienced in a car, as you go into a curve, you're going at a certain speed. If you take a tight turn, just take your foot off the brake and the gas pedal. If you take a tight turn, it feels like you're speeding up. Oh, it's because you are. Because your radius, the distance from you to the radius of your curve drops and sort of slingshots you a little bit. From a force point of view, as I'm spinning around like this left arm's not really contributing much to my speeding up, because as I bring this arm in, it basically is just coming straight towards me. My right arm, though, as I'm spinning around this way, has to come all the way around. It's like I'm throwing myself into being a little bit faster. And then reverse as I take it out. Now, in the textbook, Hewitt's got a slightly different formula. I'm pretty sure he's got this one, but he's got a slightly different one, which has confused students in the past. If I just have a mass on the end of a string that's being slinging around, the moment of inertia, the angular momentum is the moment of inertia times the angular speed. I'm going to drop the vector notation for right now, just to make life simpler. The moment of inertia of a blob at the end of it, assuming all the mass is right there, is just mr squared. That's mr squared. And omega, we've talked about this before, v is equal to omega r, so omega is v over r. So it's v over r. Now the derivation is not as important as where we end up. That r cancels out with that one, and I'm left with mrv, or I think as he writes it, mvr. So in the specific case of I have a blob of mass that is small compared to the size of the radius there, a blob of mass going in a circle, that's the formula. Now why is this confusing to students?
Too
And not only that, but too many letters can show up in two different formulas.
Oh.
The formula for centripetal force is mv squared over r. The formula for angular momentum, mvr. A student gets on a quiz and suddenly they are faced with, oh, I'm given mass, speed, and radius, or a distance. If your mind is blanking, you're gonna grasp at the formula that has mv and r in it. And there's two of them. Please be aware of which one's which.
So the first one is centripetal force and the other one is what?
Angular momentum for a single mass traveling in a circle.
Mm-hmm.
This would be the force required to get that mass to travel in a circle.
I'm just trying to figure out why they're making things so complicated.
Because physicists hate writing.
Hmm, okay.
But it's a whole lot simpler than, reading the history of mathematics, and they talk about that the shorthand notation didn't exist hundreds of years ago. So everything was written out. And I was thinking, wow, that would just be a huge pain to have to read out a formula.
Brains.
The giant chalkboard.
Yeah.
Big brains is just working. It's a beautiful thing though, how the brain can work though and get all of that stuff and put it in if that's what we put it in, or what we put in.
It'd be easier.
Would English be easier?
Yeah, because you could actually know what the thing is instead of like, I thought a mega was like the little circle with a line through it. That's the last thing I heard about the whatchamacallit, but I had no idea that it was like an upside down 3 with a, yeah, I didn't know that. So it would probably be a lot easier if you could just read it out instead of the abbreviations.
Okay.
So they were probably smarter back then.
I think what you're saying though is that our minds don't work the same way.
That's what he said, cause we've simplified things to kinda keep us at a level.
All right,